Hello, what's going on everyone? Welcome back to this channel. My name is Study Master Guide, and today in this video we're going to be talking about master theorem. So what is master theorem? Where do we get to use it? Why do we use it? That's what we want to look at in this video. The master theorem is an approach which we use to analyze time complexities of different algorithms, specifically the divide and conquer algorithms. Examples of divide and conquer algorithms include the merge sort, binary search, and many others out there. And to use this master theorem, we start off with a specific recurrence relation. We obtain these recurrence relations from the problem statement, and we'll be looking at examples in this video, so stay tuned. Okay, so we want to get to understand what a recurrence relation looks like, and this is an example of a form of a recurrence relation. So we have t into the bracket n equals to at into brackets n over b plus fn. So what are these terms that we're looking at here? So t into bracket n is what we're calling the time complexity. This is what we're trying to figure out, the time complexity of the algorithm. And what is this n? N is just the size of the problem. And then A stands for the number of sub-problems. So divide and conquer algorithms work by dividing a big problem n into smaller sub-problems, right? So for example, we can have n over 2, we can have n over 3, we can have n minus 1. So they're all divided into sub-problems, and later on these sub-problems are combined to form the solution. Once the solutions of the sub-problems are combined to come up with the final solution. B stands for, so that A stands for the number of sub-problems. B stands for the number or the factor by which we divide the big sub-problem to get the smaller sub-problems. For example, B here could be 2, here 3, and here B could be 1. So the factor by which we divide the big problem n into smaller sub-problems. Then Fn is the cost of dividing and combining the solutions. So whenever we divide and conquer algorithms, like we say, you divide a big problem into smaller sub-problems, and then you will later combine them, right? So the cost, the amount of work done for dividing and then combining them later on, that is factored in the Fn. Yes. So when we're working with master theorem, we need to have three cases in mind. We've already seen the general recurrence relation for the master theorem, t into bracket n, a t into bracket n over b plus fn, and we've gotten to understand what these terms stand for. So we have like some three cases that we need to look at. In case 1, we're saying that if fn, this term over here, if fn is big O of n to the power of c, whereby c is less than log to the base of b of a, then we'll have a time complexity of this form, right? So we're going to be seeing examples here, and we'll get to understand it even better why we're saying fn is big O of n to the power of c. But I want you to remember this part as this specific part, as it will help us to decide if a certain recurrence relation belongs to case 1 or case 2 or case 3. So for case 2, again, here we're having if fn is this, whereby c, this time c equals, here it was less than, then we'll have a time complexity of this form. And finally in the third one, whereby c is greater than, then we're going to be having a time complexity of this form. Okay, so let's start with like the problems. So we have an algorithm A which solves a problem by dividing it into 5 sub-problems which are half the size. Let's remind ourselves of the general form of the recurrence relation. So t into bracket n equals to a t, okay, 1 minute, a, okay, t into bracket n over b plus fn, right? So in this first algorithm A, we're saying that this algorithm is a divide and conquer algorithm. It solves the problem by dividing it into 5 sub-problems. Remember, A is the number of sub-problems, so this here will be, instead of 5, actually this here would be A, okay? And then next up, we're saying the problems are half the size, so B would be 2, right? And then recursively, and then combining the solutions in linear time. So this is Fn, and linear time just means big O of n. Yeah. Let's check out another problem. Algorithm B this time solves the problem by recursively solving 2 sub-problems. So 2 is A, and the problems are of size n minus 1. So we can have n minus 1 over 1. So in this case, B would be 1. And then combining the solutions in constant time is big O of 1. So this is Fn. Okay, one last problem, we have algorithm C, which solves a problem by dividing it into 9 sub-problems. So that will be our A, of size n divided by 3. So this would be B. And then recursively solving them and combining them in this. So big O of n squared, that is our Fn. So let's look at these problems individually on a larger scale. So we start with algorithm A. We say that divide into 5 sub-problems, and then half the size, so this would be B, and then solves each in linear time, big O of n, and this is our Fn. Before we look at the deduced recurrence relation, let's just remind ourselves of the form, the general form, A t of n over b plus fn. Okay, so we've already found what A is 5. That's what we start with, 5t into brackets n divided by 2, which is b, and then our fn is the linear time, and that's what we put here. So we have the recurrence relation. We now can find the time complexity. We just need to know if it's in case 1, case 2, or case 3. So remember that thing that we were saying in case 1, that fn equals to O big O of n to the power of c, whereby c is less than log to base b of a, right? This was case 1. So let's see if it's going to match this case 1 of the master theorem. So this is the recurrence relation that we just deduced from the problem statement, and we're checking. So here c is just 1, n to the power of 1, and therefore we have like c is 1, right? Yes. And if we try to check log, so we know that c equals 1. What about log to base b of a? Log to base b is 2, a is 5. So 2 to the power of x equals 5, and we get x is approximately 2.32. 1 is dash 2.32. 1 is less than 2.32. Therefore, this suits case A of the master theorem, and we are going to be using this time complexity of case 1 of the master theorem. So we just have to put in our values, n to the power of log to base b of a, and we've already solved this part to be 2.32 approximately. So therefore, our time complexity, or the time complexity of algorithm A, is big theta of n to the power of 2.3. Let's look at another example, problem B, algorithm B. We did say that it solves 2 subproblems, so that would be A, and then subproblems are of sizes n minus 1, and we did say here divided by 1, so just 1 is B, and then combines the solution in constant time, that will be big O of 1, so this is our Fn. And we end up with this recurrence relation, whereby t into bracket n equals to 2t, this is the A, into brackets n minus 1 divided by 1, which happens to be our B, and our Fn is the constant time. So let's deduce the time complexity for algorithm B. Just our recurrence relation just derived from the problem statement, and again we have to ask ourselves, in this case here c is also just 1, so we need to check, is c less than log to base b of a? Log to base b of a, in this case b is 1, a is 2, therefore what do we get? 1 to the power of x will give us 2. 1 to the power of what will give us 2? Really, 1 to the power of nothing. We really can't get to from 1 all the way up to 2, right? So 1 multiplied by itself, how many times will give us 2? We really don't have an answer. That's why we end up with undefined here. And therefore, whatever undefined is, it's still bigger than c, which in this case is 1. Therefore, c is less than the undefined, and therefore we default to case 1 of the master theorem. And again, we follow this time complexity of big theta of n to the power of log to base b of a, and we end up with an exponential time complexity. Last problem here, this is problem C. So algorithm C solves a problem by dividing it into 9 subproblems, and each subproblem is n over 3, so B is the factor by which we divide the big problem n into smaller subproblems, so B is 3, and it combines everything in big O of n squared, so this is our Fn, and we end up with this recurrence relation, right? So we have t into brackets n equals to 9t into brackets n over 3, and then big O of n squared. Again, we need to derive the time, so we need to get the time complexity by looking at which case it belongs to. So again, this is just the problem statement that we had for algorithm C in the previous page, and we just want to ask ourselves again, C, what's C? C in this case is 2. What about log to base b of a? What could that be? So 3 to the power of x equals to 9, which is just 3 squared. So x equals 2. Therefore, we get that C equals 2 log to base b of a, so 2 equals 2, therefore C equals to log to base b of a, and this corresponds to case 2 of the master theorem. And in case 2, the time complexity follows this form over here, and thus we now just have to plug everything in and solve the problem. So we've already solved this part, n to the power of log to base b of a. This is just 2, and we end up with 2 here, so we have big theta of n squared. And remember here we're having the log to the power of k plus 1, so k is the exponent of the logarithmic term, and in this case k equals 0, so 0 plus 1, we get log to the power of 1, which is just log, therefore we have log n, and we end up with our time complexity of t in the brackets n, big theta of n squared log n, which is a polynomial. So in comparison and in conclusion, we get that algorithm A has a time complexity of approximately big O of n to the power of 2.32, algorithm B is exponential time, and algorithm C has a polynomial time. So which one would you choose between these 3 algorithms? Remember, it depends with what type of problem you're solving and what are the amount of resources that you have at your disposal. So I do talk about this more in one of my articles, link in the description below, and thank you for watching this video, and see you again soon. Bye for now.